This is on page 114 of our workbook. To solve a system linear equation using Gauss elimination, you write the automatic matrix for the system. Use elementary row operations to write the automated matrix in row echelon form. Begin by getting the entry in row 1, column 1 to be 1 with zeros under it. Use back substitution to solve the resulting equations. Now, if you actually take it a step further and get to reduce row echelon form, that's called Gauss-Jordan elimination. And we'll compare the two. So, let's go back to our handout. Solve the system linear equation using the Gauss-Jordan elimination. Write the matrix that represents the system of linear equations. Use elementary row operation to rewrite the matrix in reduced row echelon form. For a 2 by 3 matrix, this is done by get a 1 in the top left corner. You may find it easier to first switch row number 1, row number 2. Then divide every number in row number 1 by the entry in the first row, first column. The answer is your new row number 1. That's your first step. Next, get a 0 in the lower left corner. Multiply row number 1 by the opposite of the entry in the second row, first column, and add the result to the second row. The answer is your new row number 2. Then third step is to get 1 in the entry for the second row, second column. Divide every number in row number 2 by the entry in the second row, second column. The answer is your new row number 2. And if we were just doing a Gaussian elimination, you would stop there and you can back substitute. But if you're here, you might as well just take it one more step to get a 0 in the entry in the first row, second column. Multiply row number 2 by the opposite of the entry in the first row, second column, and add the result to the first row. The answer is your new row number 1. You can then just write your new system linear equation that corresponds to the matrix and write down the answer. So let's go to our workbook. And we're going to take this a step further. Rather than do Gaussian elimination, we're just going to do Gauss-Jordan elimination. So, the first step, anytime you see a system of linear equations, you have to have the equations in standard form. So, the first one's good. 2x plus 3y equals 7. Now the second one, we've got to do some simplifying. So I'm going to need to distribute that 3. So that's 3x plus 3 equals 5y plus 4. I got to move the 3 over. So I'm going to subtract 3 from both sides. And then I'm going to move that 5y over. So I'll bring it up here. That's going to give us 3x minus 5y equals 4 minus 3 is 1. Alright, so now our second equation is in the correct form. So that is fundamental. You have to do that first. You have to get them in the right form. You got to make sure that your x's and y's are in alphabetical order on the left side, constant term by itself on the right side. Now we're ready to write our augmented matrix. So I'm going to go 2, 3, and 7. 3, negative 5, and 1. And now our first step is to get 1 in the top left corner. In this case, it's probably going to be worse if we switch around the rows. So let's keep the rows the same. And I'll tell you what, I'm going to do this a little bit differently from the book. I'm going to use lowercase r's to represent the rows I'm working with. The uppercase r is for the new row. So I first need to get a 1 here. So I'm going to do row 1 equals 1/2 row 1. So I'm doing a little bit differently in the book. The book's going to use a capital R there. I'm going to use a lowercase so that you know I'm actually operating on this, and this is what my answer is. So 1/2 of row 1. Well, we have a 2, 3, and 7, and I'm dividing these by 2. And that's going to give me my new row 1. That'd be 1. I'm going to write that as 1.5 and 3.5. So now when I write my matrix, I'm going to write 1, 1.5, and 3.5. Just going to copy down the second row as is. So let's go to step 2 of our procedure. Get a 0 in the lower left corner. So we're going to multiply row number 1 by the opposite of the entry in the second row's first column and add the result to the second row. The answer is going to be our new row number 2. So now I'm taking row 2 and I'm looking at the opposite. This is -3. So I'm going to take a -3 times row 1, and I'm going to add row 2. Let me just go off the side and write that out. So -3 R1. So multiply by 1 by 3, that's 3. Multiply 1.5 by 3, that's 4.5. Multiply 3.5 by 3, that's 10.5. And now I'm going to copy everything down row 2. And this needs to be negatives because it was a -3, my bad. So I'll copy everything down row number 2. And when I add this, that gives me 0. That gives me -9.5. And that gives me -9.5. Now remember, row 1 is staying the same. So this is 1, 1.5, 3.5. This is 0, -9.5, and -9.5. All right, so now we've completed step 2. Step 3 is we want to get 1 in the entry for the second row, second column. We're going to divide every number in row number 2 by the entry in the second row, second column. The answer will be your new row number 2. So I want to divide everything by a -9.5. Or if you want to write as a multiplication problem, you can say we're multiplying by 1 over -9.5. So when I do that over here, I'm taking each of these entries and I'm dividing by -9.5. It's going to give me my new R2, which should be 0, 1, and 1. Now, if we were just doing Gaussian elimination, we would just stop here. We'd say y is 1, because this would translate into y equals 1. And then this would be x plus 1.5y equals 3.5. Replacing y by 1, that would give you 1.5 times 1 is 1.5, so that'd be x plus 1.5 equals 3.5, and then you solve for x. But since we're here, we're just going to take the next step, do the Gauss-Jordan elimination. Just go ahead and do step number 4. Get 0 in the entry for the first row sec column, multiply row number 2 by the opposite of the entry in the first row second column, and add the result to the first row. The answer will be your new row number 2. So I have 1.5, so what I want to do, I want to get my new row number 1. It's going to be a negative 1.5 times row number 2, and I'm adding that to row number 1. So let me do it over here. 1.5 row number 2, that's 0, negative 1.5, negative 1.5. And now I'm going to just rewrite down my row number 1. It's 1, 1.5, 3.5. So that's my new row number 1. So that's 1, 0, 2. Excuse me. So let me go ahead and rewrite my matrix. Row 0, 1, 0, 2, 0, 1, 1. So my equation here would be x equals 2 and y equals 1. So my solution then is the point 2, comma 1. Now you can check this. If I replace x, go back to my original equation, replace x by 2, y by 1, that's 4 plus 3 is 7. Do the same thing here, replace x by 2, 2 plus 1 is 3, 3 times 3 is 9. Replace y by 1, 5 times 1 is 5, plus 4 is 9. So it does check. So that would be your answer. Now, section 11.2 talks about inconsistent and dependent systems. We kind of saw a little bit that before. Inconsistent systems, if it's a system of 2 equations, you're talking about 2 parallel lines. If you're talking about 3 equations and 3 unknowns, you're talking about a graph of a plane. And if you have a system of 3 equations and 3 unknowns, they all have to intersect at the same spot in order to have a solution. If they are parallel planes, or 2 of them the same, the third one's parallel, there's not a point that's in a common 3, that would be no solution. Similarly, if 2 of the 3 intersect, but not all 3 at the same spot, that would be an inconsistent system. And what happens when you try to solve an inconsistent system going through your row operations, what's going to happen here is on this last row, you're going to get zeros on the left side, and then you're going to get a non-zero number on the right side. And so this means 0 equals 56, which is impossible. So that tells us that this system's inconsistent, it's a contradiction, and there's no solution. Now, on the other hand, we've seen where they're actually the same line. So if we're asking to solve a system of dependent equations with 2 variables, so first thing we do is we get in standard form, and then what you might want to do is also clear, I'm not sure why they're doing this step, but hey, we'll humor them. We wouldn't normally do it this way, but okay, multiply by 100, clear out the decimal. And just getting everything in standard form, so I got to bring that x over, subtract x from both sides. So now I'm going to write down my matrix. And then we want to get 25, make that a 1, so divide everything in row number 1 by 25. See, I would have just divided, I would have kept it this way and just divided by 0.25 and done it on a calculator. But that's the way they did in this example, so we'll humor them. So that gives 1, negative 3, and 4. Now to obtain a 0 in the second row first column, I have to multiply by the opposite. Well, if I multiply that by 1 and add, everything zeroes out. And if everything zeroes out, then this reduces to one equation. Every point on the line is a solution to that equation.